All right, welcome everyone. This is the Introduction to Alternative Energy lecture over Chapter 1. The book that we are using for this is Renewable Energy Power for a Sustainable Future, 4th edition. If you are trying to follow this along or follow along with us from the video, you will not have just taken a quiz, but for the rest of the people that are in the class, at any point in time throughout this lecture, if you feel that you read something different in the book, please stop me. And when I say that, I'm saying that because the PowerPoint slides that I'm going to be showing you, I first created in 2011 when I was a student, and then I updated them a little bit about 4 years ago. The world of energy has changed. In fact, the numbers that are in your book will be slightly different from the numbers that are in my chart. Since the ones in our book are current, that will always win out in a debate about a proper answer on a quiz or a test. In other words, if my quiz was created in 2011 and the percentage of coal versus oil versus natural gas has changed, and your answer is more accurate, and I've counted it wrong, feel free to let me know. I'll even go so far as to say if you could find current data that is even more accurate for your answer you gave than in the book, I will allow you to use the IRNEA, that's the IRENA, or the IEA websites. IRENA stands for the International Renewable Energy Association, and then the IEA is the International Energy Association. I don't want to lead you to believe that they are competitive organizations, but right now that's kind of what we're studying. What's the difference in renewable energy, IRENA, International Renewable Energy Agency, versus the IEA, the International Energy Agency? What makes renewable energy different from other energy? Anybody? Can't use a word to describe itself. So how would we define it? That's a lot of words. There's got to be a simpler way for us to define that.
To quote Sorensen in 2000, energy flows which replenish at the same rate as use.
There you go. It is not possible for you to use the energy at a rate faster than it is replenishing itself. In other words, if I use every bit of the solar power that came from the sun and struck the earth today, would it burn out tomorrow? We've used it all up. The sun went out. No. Okay. It is going to renew at as fast or faster than we can extract or use that energy. So when the IRENA, International Renewable Energy Agency, talks about energy futures, that doesn't mean they're ignoring fossil fuels, but they are approaching the problem from an understanding that renewable energy is different. It's going to have different growth rates. It's going to have different investment rates. It's going to have different government support in different parts of the world. Whereas energy in general is everywhere. Can somebody try to name an industry for me that does not use energy in that industry? One time somebody said the psychic industry. I'm like, no, you're still burning calories. It's still energy. You, as a manual laborer, still have an energy balance. You have to intake as many calories as you output, or else you lose weight. Okay? If you intake more energy than you are outputting, then you potentially gain weight. Isn't that one of our major struggles in modern times in America? We want to eat steak every night. We really don't want to have to go like work in the hot sun for a daily job. Our natural bodies, we crave sweets that taste good to us. So this energy challenge, guys, that's an economic challenge on all levels of our economy and almost all industries when we talk about energy, because energy is an all-encompassing term. So the IEA, the International Energy Agency, approximately every 2 years, they do what's called the World Energy Outlook. And throughout this class, we're going to be frequently studying the 2020 World Energy Outlook. It's the most current, whole, big picture that we have of energy today and in the future. And one of the things that you'll find that the IEA, are primarily funded by the fossil fuel industry, because the fossil fuel industry is the primarily provider of our energy. So they fund this organization, yet even this organization, funded by primarily fossil fuel dollars, recognizes that wind and solar power are not only the cheapest way to produce electricity in the world today, they are the cheapest way to produce electricity today that we have ever had in mankind's history. In other words, as of 2020, we've never been able to, when you account for inflation and all of the costs involved, we've never been able to create electricity cheaper than today, and we're doing that cheapest via wind, onshore wind specifically, and solar. Offshore wind is very far behind the onshore wind. Yes, sir.
That first acronym that you said,
IRENA, International Renewable Energy Association. Yep. So, finish my attendance and click on over here so I can follow along. Okay. So we've kind of defined renewable energy. We are using it for human purposes at a slower rate than it replenishes itself. Who can name one renewable energy source? Cameron? Wind. Brian? You got to be more specific. Besides sun, there's two primaries in our books. There's solar thermal or solar PV. We're going to use both of them since you said the sun. Name another one?
Tidal.
Tidal. All right. Can you name another one? Geothermal. Name another one. He said yours right before you did. That's an energy type, not necessarily a renewable form of energy, but there's one that primarily uses gravity. What falls? We extract energy from it. It'll get you wet. Hydro. There we go. Hydroelectricity. You think of another one? We're running out of them here. No? Tidal? Okay. Wave and tidal are different. So yes, tidal and wave are different. Yep. Biofuels. That's the one that most of you guys, that is the largest experience of renewable energy that any of you had. How many campfires have you had in your life? How many of you loaded a wood stove in your life? You've used biofuels. If you pump gasoline at the pump, I'm pretty sure most of those pumps have ethanol in them, a quantity of about 10%. So those are all biofuels. In fact, biofuels are really the only energy source that even comes close to competing with fossil fuels for the scale that we use them in. I will astonish you in this class some of the facts about biofuels. Right? There's some experiences that most people in the world have using biofuels that most Americans do not have. I graduated from this program in 2011. And in 2009, I believe, I took this exact class. And I learned that at that point in time, like a third of the world's population still cooked their food over an open flame. Okay, by biofuel. What do you think the number one biofuel to cook food is in Africa? Not a lot of trees out there, guys.
Probably just dead shrubs. Or dead
Grass. No. Poop.
Yeah.
Dung. Does it sound appealing to have your meal cooked over poop? Does it sound healthy to have poop in your kitchen where you're cooking your food? That led to one quick bit of research to realize that many, in fact, the leading cause of death of children in extreme poverty in Africa under the age of 5 is diarrhea. They poop themselves to death because their foods are frequently cooked in unclean environments because they need the heat to cook. But the only biofuels or the only energy sources that they have are dried dung that is collected by hand from the deserts or from the savanna or from the plains. It is grass. It's that an animal called a ruminant has eaten that grass and then pooped out material that is still burnable. All right. So pretty much Everything that you guys just mentioned is ultimately solar powered. And you're going to trace back these energy forms. Let's use wave, for example. That's the one that there's a lot of steps between. Where do waves come from in the ocean?
The gravitational pull from the sun. Or
That's tidal. That's tide. That's our tides. But the waves themselves that crash up on the shore, where would those come from? No, that's tidal. That's what he's talking about. Yeah, gravity has nothing to do with our waves.
So the waves would come from a storm or something.
There you go. They come from a change in air pressure, high pressure, low pressure. Take a glass of water that's perfect calm and blow on it. What happens?
Creates a wave.
It creates a downward pressure and waves that go out. Now take and continue to blow on it. The wind catches that wave and it pushes it, makes it go faster and higher and faster and higher. All of our waves are actually wind driven. They're wind powered. Wait a minute. What powers the wind?
So
Key, it's not gravity. Just kidding. It's what?
that's the sun.
It is the sun. Uneven heating of the Earth's surface. Hot air wants to rise. You can't have no air, so that pulls in colder air. You create this natural circulation. Spin a basketball on your finger. Think of the air on that ball. Around the equator, it's moving rapidly around and around. At the poles, it's hardly moving. So we have this constant reaction of the air called the Coriolis effect, to where parts of the air are being grabbed by the earth and moved. Other parts are being lifted up into the atmosphere due to the rising hot air. Other parts at the poles have sinking air because the air gets cold. We have wind that is completely powered by the sun. Can anybody think of an energy source that's not powered by our sun? Nuclear energy. All right, now that's one of the energy forms you guys didn't mention, and I was going to get you on it. Why did none of you say nuclear energy for a renewable energy source?
It's debated whether or not it can be classified.
It's not debated as no. It's debated if it can be classified as sustainable. It is not debatable. Nuclear energy is not a renewable energy source. The media will make the mistake commonly. Friends, even you guys might accidentally, you're not trying to teach your family, you're trying to get them to open their mind. But nuclear energy is not renewable. When we run out of nuclear material on this planet, then we're out. We don't get to make more nuclear material. If we do, we end up putting more energy into that making of the nuclear material than we can extract out of the nuclear material. Now, yeah, there you go. Okay. Now, we can do cold fusion, and that's the concept of, in a controlled manner, we're smashing atoms together like two hydrogen atoms to make a helium atom. Now, that could potentially be done in an unlimited quantity. But when we talk about nuclear energy, we're talking about radioactive material that is in the crust of the Earth. We mine it, we refine it, we extract energy from its nuclear decay. Interestingly enough, you guys who listed geothermal, I think somebody listed geothermal. Geothermal is powered primarily from nuclear decay within the Earth. It is debatable if it is a renewable energy or not. Most people agree it is. The reason being is we can't extract the energy from the Earth faster than that nuclear decay is happening.
Isn't the nuclear decay just normal decay of, per se, just organisms, actual radioactive?
No, we have huge quantities of highly radioactive material in the crust of our Earth, and they are breaking down. Fortunately, we have enough Earth that we're not being radiated from that breakdown. There are some places that nuclear material is in high enough quantity and close enough to the surface of the Earth, like in the Boreal Mountains, I believe, that you can have Geiger counters that naturally show high concentrations of these nuclear materials. But there is enough of it breaking down that's part of why our Earth should not be warming. Naturally, we have less and less of this material. So naturally, we should be cooling off more and more and more. Granted, these go through cycles, but as a long-term, eons picture, the Earth is not and never should be in a larger warming cycle, per se. We have smaller warming cycles. particles. That's completely natural. But as a whole, our radioactive material is getting less and less and less throughout the crust of the Earth because it's continuing to break down. Nuclear is a big debate, and we'll have that debate in this class. Is nuclear truly sustainable? I mean, at our current rate, we have like 10,000 years of nuclear material that we know of, and we can access. How much material do we have deeper that we can't get to right now with our current technology? But we would 1,000 years from now. 1,000 years ago, we didn't have any technology really compared to our current technologies. And so most people, most scientists and engineers do consider nuclear energy to be a sustainable energy source. All right. So let's go on over here and scroll on down a little bit. Defining sustainable energy sometimes can get a little bit harder, per se. Renewable energy is obviously derived from the natural sources that are naturally replenished. However, some organizations classify nuclear. We're just talking about nuclear. Some organizations classify nuclear energy as renewable, but it should be considered an alternative energy, not a renewable energy. That's the clarification on our nuclear. And then last is sustainable. Sustainable energy is an energy source that meets the design load requirements without using up the source. An example might be a paper mill that regrew its own trees. It's very important you understand the deeper meaning of the word sustainable rather than just trying to apply the word sustainable to energy. Sustainability needs to be applied to many, many fields throughout the world. Home building. That's another thing that in my daily life I apply sustainability to. We all need a place to live, and we all want comfort in that home. And if you don't build your home right up front, then you quickly end up either having to spend large amounts of maintenance, large amounts of energy, or tearing the home down and completely redoing it in a pretty short time period. In fact, with Hurricane Ida that has just come through, I'm curious to see how many of those homes that were built after Katrina right now end up needing to just be completely torn down and rebuilt because they were not built sustainably for the local climate, environment, and location in which they were planned, designed, and constructed. All right? So sustainability is very important in the word sustainable. Sustainable means that the design load requirements are being met without using up the source. Solar is the easiest one that I can give you an example of. There's just no way that you can use up the sun's energy faster than the sun is going to give you energy. All right. The sun's energy is nearly constant. It's not always constant on each place of the Earth, but it is almost constant on the Earth. Now, it does change based on our time of year. Can anybody guess what time of year the Earth has the highest solar radiation? Now, this whole time of summer and winter, you guys know that like Australia has summer when we have winter and vice versa? Right. So when we're talking about the Earth, it can't have anything to do with seasons. The whole Earth is experiencing this. Is there a certain time of year that the Earth has a noticeably larger energy absorption from the sun? Nobody wants to guess?
Is it like based on the orbit?
It is. Is there a time in our orbit that our orbit is closer to the sun? And if so, how much closer?
It's ovular.
It is. It's an oval shape. Do you know what time of the year we are closest to the sun? Summer? Because it's hotter where we are?
Well, that has to do with...
Correct. Our summers, our seasons have nothing to do with our distance to the sun. That's one of the largest rumors that is fake, completely fake. In fact, in our summer, we are 2 million miles closer to the sun than in our winter. Our pattern of elliptical orbit varies from 91 million to 93 million miles distance from the sun to the Earth. January 6th, I believe, is the point in time that we are closest to the sun. And on that day, on average, we receive 6% more radiation on Earth, meaning that the southern hemisphere, Australia, they get cooked, guys, because they are pointed at the sun. They get long days, and because of our pattern of orbit, they are 6% closer or 6% larger in that solar radiation gain. Think about where the world's deserts are located. Almost all of the largest deserts are either at the equator or south of the equator. Right? It's not an accident.
Yeah, there's only one California, Nevada, Arizona area.
In the United States is what you're saying? Yeah.
That's the only
So we are going to measure all of these energy forces using certain units. Learning of these units is extremely important. I'll start with the easiest one. What units do we use to measure voltage? Volts. So easy that I tricked you already. That's the way I work, guys. Okay. But it's literally that confusing sometimes because you think that couldn't be. He couldn't have given me the answer in the word of the question. Andrew's not that nice. Okay. Normally I'm not. All right. So yeah, voltage is measured in volts. Okay. Volts in an electrical system is extremely similar to the pressure in a hydraulic system. What's a hydraulic system?
What makes the crane arms?
What is it? Thank you. Perfect answer. Pressurized fluid. Do we have any hydraulic systems in this room?
Let's say your desk.
Yeah, all of that is pressurized fluid. Okay. Now, there is things called hydraulic cylinders, and that's a whole new level of hydraulic pressure. But I'm more talking about the basic plumbing system. Okay. Whenever you think of the basic plumbing system, it has to have a power source. What created the pressure inside of that system? Let's call it a well pump. The pump is pumping the water from the ground up into a pressure tank. That pressure tank would be kind of like a battery because it's storing the pressure. All right. So in the electrical system, that would be a generator. The generator is creating an electrical pressure, and it could charge a battery, similar to like that pressure tank. The pressure inside of those pipes is water pressure. The pressure inside of the electrical conductors is electrical pressure. It is so similar to the fluid pressure, it's unbelievable, guys. Think of it this way. You ever try to put the magnet side of north and the magnet side of north together and push them together? The closer you get them, the more they want to come apart. That's what electrons are doing inside of that conductor. They want to get the heck away from each other. They hate each other. And so they are constantly pushing on each other in all directions. The amount of pressure that we are forcing them to is electrical pressure. It's called voltage, and it's measured in volts. How many of you guys have had a high amount of voltage course through your body? I got one, I got two, I got three, yeah, I got four. You all have. You've had static electricity? That can be 100,000 volts. It is not the voltage that kills you. Think of it this way. If I have a fire hose and I have a garden hose, and I've got this garden hose and I'm spraying you with it, it's summer, it's hot, oh, it's fun, I'm cooling off, it's enjoyable, and suddenly, dude flips open the fire hose and blows you across the parking lot. There's more than one quality in that fire hose. It's not just the pressure, it's the volume of water. All right? That's what actually harms a human being is the current. What units do we use to measure current in an electrical system? Amps. That's exactly right. The amperage of the electric system is what will kill you. And it takes much less than 1 amp. In fact, we're talking like 0.03 amps before it can be deadly. I actually have a device over here that when we stop recording, we're going to get to plug in. It is a static electric generator. We will let you feel yourself charge and discharge so that anybody that hasn't experienced electricity, knowing that they're being shocked, gets to feel it. It is important for safety because sometimes you are getting mild electrocutions while you're working on electrical equipment and you think the electrical equipment is completely de-energized. If you can't recognize the difference in that feeling, it could lead to your death. All right. Some people have never been shocked before. Do what? Yeah, congrats to them. All right. So we have volts, which represents our electrical pressure. We have amps, which represents our volume of electrons. In the hydraulic system, that would be how much water is coming out. Okay? We have to have things to turn these on. The valve in your kitchen sink is the exact same thing as the switch in your light bulb. They are completing a path and they are allowing the flow of water or electrons. When I flip that light switch, the electrons course through the light bulbs. They do work. Okay, give us light. Whenever the water runs out of the sink and I wash my hands, the water is doing work. It's washing my hands. The water and the electrons both must return to their source. That water flows down the sink, down the drain. Those conductors are the same concept. You have a wire that leads back to the generator. You have a pipe that leads back to a septic tank, which leads to a leach field, which leads to the earth. The water started in the earth. The water had energy put into it. It did work, and it returns to the earth. In an electrical system, the electrons had energy put into them. They passed through a switch. They passed through a load. They did work, and they returned to their generator or to their source. The amount of power, almost made a mistake there. The amount of power is the volts times the amps. And power is measured in watts. And what else? What else do we measure power in modern society besides watts? Vroom, vroom. Horsepower. So many times people are like, well, horsepower and watts, they're nothing alike. Liar. 746 watts is exactly equal to 1 horsepower. How many of you guys feel that you're powerful? If I put you on an electric generating bike over here, how many watts of electricity could you generate? 4. Well, think if a horse can output 746 watts sustained, because that's what a horsepower is how much work can a horse do constantly, okay, without having to take a break or anything. If they can put out 746, I mean, do you think you're a half a horse? I'm a half a horse kind of guy. I got at least about 375 watts in me. You're a quarter horse, okay? I was waiting for it. I was setting you up. Good job. Yeah, quarter horse. You're a quarter horse, man, and I believe it, okay? Lance Armstrong could put out about 350 watts. He's a professional athlete. In fact, world-renowned. I mean, that's even on drugs he can put out 350 watts, right? The average adult athletic male can put out about 250 watts on a power output scale. We're about a quarter to a third horse. Okay. Now we're starting to put some pieces together in power and horsepower and electricity. They're all the same thing, guys. They're just in a different form. In fact, in your reading in chapter 2, you're going to learn about the laws of thermodynamics. Energy cannot be created nor destroyed. It can just change forms. And that's what we do with electricity. We can take heat and turn it into electricity. We can take electricity and turn it into heat. We can take motive force, you pedaling that bicycle, and turn it into electricity, and then turn that electricity into heat. We can turn it into light. We can turn light into electricity. We can turn electricity into motive force. In other words, the sun can power a solar panel, can power a motor, and can power your bicycle. We can just change forms, but there is always loss. Always. loss. And that's the second rule of thermodynamics, is you will always have losses. There's no such thing as a perfect heat engine. So the last thing that we need to talk about is energy. Energy is power over time. Okay? And you're going to make this mistake throughout this class when we're talking about different things, and you get power and energy confused. I've been in this industry for 12 years or something. I still occasionally make a verbal mistake, and I say the words power when I'm meaning energy, or vice versa. That horsepower is an instantaneous number. You ever hear these guys with their big dualies, and they take off from here, and it revs way up, shoots the black coal out, the smoke, and then when they're flooring that, let's say they're like, yeah, my truck's got 350 horsepower. Does it have 350 horsepower the whole time that they're giving it gas? No. In fact, I bet this gentleman knows right here at approximately what point in that 6,000 RPMs are they actually putting out that 350 horsepower. You do some racing, don't you? Yeah. What would you say if you got an RPMs of 0 to 6,000 RPMs on a standard internal combustion engine? Where is it going to max out its power? Yeah, okay, all the way up there. And so it takes a long time before you get to that maximum power. That's the great thing about electric motors, guys. You get that electric motor and it can put up its full torque at 1 RPM. Yeah, it reaches its full power. The challenge is that power is an instantaneous number. And so I don't really know how much energy was used until I add up all of that. So let's think about a light bulb for a minute. A light bulb uses 10 watts of electricity. What that means is that if you're pedaling, you have to put 10 watts of energy into the generator in order to make the light bulb light up. If you light that light bulb for a full hour, that's 10 watts times 1 hour equals 10 watt hours. Pretty simple, right? If I had a 5 watt light bulb and I ran it for 2 hours, that'd be 5 times 2. That's the same amount of energy, even though it was only half the power, because it took twice the time. Are we starting to understand the difference between energy and power now? Energy is measured in watt hours, and it is how your electrical bill is billed to you. Power over time. Sometimes you're using a massive amount of power. Sometimes you're not using hardly any power whatsoever. So they add that power over time up, and you have kilowatt hours. So these prefixes that we use are very, very important. We're all the way down to the engineering prefixes. We know what a watt hour is, but 1 watt hour is not much. It's a tiny amount of power. In fact, you are billed, if you have Numac Electric, you are billed 9 cents per kilowatt hour. So that's 9 pennies for every 1,000 watt hours that your home uses. If you use Liberty Electric, it's about 12 cents per kilowatt hour. That seems pretty cheap. That's just not much power. The average home uses around 11,000 kilowatt hours per year of electricity. And so it's a little under 1,000 kilowatt hours per month of electricity. When you do the math, that's around $120 plus some fees, connection fees per month that the average home uses in electricity. The problem is we're starting to get into huge numbers, like thousands, tens of thousands, millions of kilowatt hours. So we change these from watts into kilowatts, from kilowatts into megawatts, megawatts into gigawatts, into terawatts, and petawatts. Those are the different wattages that we use. And there is a conversion chart that if you guys aren't, there we go. If you guys are not familiar with, you want to become familiar with. If you have had a math class, you have had a physical science class, you should have already seen these. The ones that you absolutely must know is 1 kW is equal to 1,000 watts. We're right here, okay? I don't think I need to, well, let me rephrase that. I will not, in this class, use deca or hecta watts. We skip those. We go directly to kilo. After that, we followed this trend all the way to peta. Kilo is 1,000. Mega would be 1,000,000. Giga would be 1,000,000,000. Tera would be 1,000,000,000,000. And peta, I don't even know if I got a word for it after that. Okay. Do what? Quintillion, quad something or other. I just remember quadrillion, quintillion, something like that. Yeah. This is not a math class. We'll call it the peta. There's only a few incidences that we talk about petawatts, and that's when we're talking about total global energy consumption. Okay. Only incidences that we're talking about numbers that large. You absolutely need to be able to be comfortable with going from megawatts to kilowatts to gigawatts to all of it, because I'm going to give you answers. Let me phrase that. I'm going to give you information in multiple formats. This home uses 1,000 kilowatts per day. Okay, this business uses 2 megawatts per year. When I combine the two, what size of a solar electric system is needed? So you need to be able to convert these so that you can add them, subtract them, and do math with them. Is there anybody that would like me to give a couple of basic examples of what a conversion problem might look like on a quiz or a test in the future for these? It literally is as simple as I write the word, I write 1,000,000, 1,000,000,000 watts. How many megawatts is this? And you figure out how many megawatts. Oh, that's 1 megawatt. Okay, how many kilowatts is that? Well, that would have been 1,000 kilowatts. Do I need to do any practice problems for that? No? Okay, that saves us a little bit of time. Is there any questions on these conversions at all then? No? All right. Okay, we're ready for the law of thermodynamics. So I am going to go ahead and cut my recording off for now.